Polyatomic ions, you just have to memorize them. So things to memorize. What do you mean things to memorize? You should memorize yourself. You want me to like test you? Come on, Hank and Takashi. How to do homework. Like which ones? Acids, gases, polyatomics. Those three. All right, pretty good list for now. If you guys have other things you want to talk about, feel free to type them in. Why hydrogen bonding works, that's part of intermolecular forces. So if you look right next to the chat little pod, we'll be going through polarity, AB notation, hybridization, intermolecular forces, which talks about boiling and melting point, and ionic naming. Aqueous stuff, for now, is just the acids. 6 acids that you have to memorize. All right. Number 6 on the worksheet review today, please. I don't know what number 6 is, so you're going to have to type it. All right, first thing, polarity. I guess before polarity, I'm going to go with AB notation. So real quick, with all the shapes, what you need to know, the shapes are linear. There are 2 ways to get linear. For the AB notation, it's AB or AB2. The bond angle is 180. And then we have, so it'll look something like either like this or I guess I should draw the Lewis dots for them. So it could be like HCl or CO2. Always a nice classic one. So that's linear. Then we have bent. AB2E1 or AB2E. Pretty much it just has those electrons. What's the bond angle for bent? Nice. 105. H2O. It's a bent structure. Then we have trigonal planar, which is AB3. So what we did was this. Oh, 105, 120. Trigonal pyramidal. AB3E, 107 degrees. That one is like, and then we'll talk about what the A, the B, the E is. I don't really know what you're asking about the AB notation. And then tetrahedral. That's AB4, 109.5. That one's like ran out of room, but I was like that. So there are 5 different shapes that we've learned about: linear, bent, trigonal, planar, trigonal pyramidal, and tetrahedral. So the AB notation, what it is, it's talking about A is your central atom. always. Usually, or most of the time, except when there's only two things. When there's just two things, you can't have anything besides linear, because if you try to attach two separate atoms together, you can only have a linear shape. So then if you look at CO2, that's our A. In this case, oxygen is our A, carbons are A, sodium. Then our B's are bonded atoms to the center. So it's always talking about the central atom. So in this case, we have one thing attached, two thing attached. One, two. So that's why it's B2 for them. B2, B2, B3 because we have one, two, three. B3, one, two, three. And then B4, one, two, three, 4. Then the E's are unshared electrons. We call these lone pairs because they're pairs and they're by themselves. They're not being shared. So in this case, our E2 would be right here and right here. E1 because we only have it right here, and then none right there. So that's just AB notation. AB notation will help you figure out the shape of everything. So I don't know exactly what question you wanted to go with that, but that's AB notation and shapes. 7 minutes talked about AB notation and shapes. So then this is a good segue into polarity because polarity depends on two things. Polarity depends on shape and electronegativity. What are the two shapes that are always polar? Nice, Alec. Bent and trigonal pyramidal. So trigonal, pyramidal, nice, and bent. So those two are always polar. And if you actually realize, trigonal, pyramidal, and bent, they're the two that have the lone pair electrons. So those two structures are always polar. So once you figure out that the molecule is trigonal, pyramidal, or bent, then you just say it's polar, then you're done. The other shapes you have to figure out based on their electronegativity. So what polarity is basically talking about is how they're sharing their electron. If something is nonpolar, that means they're sharing their electrons evenly. Whereas if they're polar, they're like polar opposites, they're sharing electrons unevenly. So if we look at the instance of carbon dioxide, so step one to figure out if something's polar would be to draw the correct Lewis dot structure. So here's the Lewis dot structure. This is an AB2 and it's linear. So then what helps you answer these questions is to know two things about electronegativity. The trend for electronegativity increases going up and to the right. So the more up and to the right you go, the stronger the electronegativity, the better it is at taking the electrons. And certain elements that we use often enough, we have that weird made up word called Foncklebrüsch. Where it's going from most electronegative to least. So this side will be slightly negative, this side will be slightly positive. So the arrows will always point this way. So then we look at carbon dioxide. Which one is more electronegative? Nice. Oxygen. So then oxygen is going to be greedier. So even though carbon and oxygen are sharing their 4 electrons, if you look at one carbon and one oxygen, oxygen is going to be unevenly sharing. It's going to hold onto the electrons a little bit more, and then it'll share it with carbon. So that means oxygen is a little bit more electronegative, so it's going to be slightly more negative. Oxygen is slightly more negative, meaning carbon will be slightly positive. Like that. So then we're going to draw our fancy arrows. We always draw our arrows from the positive towards the negative. So my arrows look like this. Arrows look like this. Yeah. So typically how I find out polarity is once I draw all my arrows, things get a little bit messy. Thanks, Alec, for helping out. There's an imaginary ball, and all I do is I transfer these arrows to this ball. So I'm going to bring this arrow here. So here's an arrow pointing this way. I have another arrow pointing here. Like that. So then if I look at these two arrows, they're both pulling on this ball. Is that ball going to move? They're basically playing tug of war with their electrons. Thinking about the overall molecule. The ball's not going to move, so I was like, hey, no. That means it's going to be nonpolar. Nice. So that means they're sharing their electrons evenly. Nonpolar. 5 points indeed. This must be Michael George. So then let's go to other random problems. So I'll give you things like try these ones out. All right, try these ones out. I'll give you some time. Oh, find the polarity. I guess if we do these problems, you should be able to do the Lewis dot. You should be able to do the AB notation. You should be able to figure out the shape and the polarity and bond angle, but bond angle you're just memorizing anyway, so try these. Dang, 29 people in this GBL. Looks like you guys really want to do well on this test. Wrong accents, Kushal. Wrong accents. Start working. Nice. Good job, Andrew. But now you have to finish your homework. Nice, Stuart. What's all the answers? Oh, you finished the homework, not this. $30 people now. Are you guys all done with everything? Yes, I was on my phone. No? Alright, I'll give you some more time because this is what I do when you guys do stuff. I spelled Sophia's name wrong. Oh, just kidding. Shanna's here now too. Just wait till you do all of them. Then once you guys do all of them, in about like 2 minutes, I'll go over the answers. Don't just type in random stuff because always too slow. Especially if you don't run to the bathroom. Just walk fast. Are you done with all of them? Alright, Bo's done. That means everyone else is done. Sydney's here with me. Is Brandon the only person who has ever fist bumped you? Yes. Hi, twins. No. Sup. Alright, things are getting out of hand. Alright, let's go over this. NH4. Should I guess you guys will stop me if you guys have questions, because I'll just do the Lewis dot structures. If you forgot the brackets, it's wrong. H4, this is AB4, this is tetrahedral. And the polarity is nonpolar. Someone enlighten Ryan, because why we need brackets? Anyone know? Yep, there's a charge. It's an ion. It has a charge, negative Kushal. It's positive. All right, so the next one. Are there any questions for ammonium ion? NH4, why it's nonpolar. Annabelle made it to the GVL. We literally just went over polarity. Right here. How do you know it's nonpolar? All right, so let's talk about this. So remember, polarity depends on what two things? Everyone's struggling to type electronegativity. There we go. Shape and electronegativity. Based on the shape, were we able to tell if it's polar or nonpolar automatically? No, we weren't. So then we have to go to electronegativity. So this is where we have to check each individual bond and check how they're sharing their electrons. So if you look at nitrogen versus hydrogen, which one is more electronegative? Nitrogen. So that means hydrogen will be slightly positive, slightly positive, slightly positive, slightly positive, and my nitrogen will be slightly negative. Meaning, which way would my arrows point? Towards nitrogen. Because remember my fancy arrows? My fancy arrows look like this specifically, because where is this going to start off? At the positive end, and this is going to start or point towards the negative end. So then if I draw in my arrows, it'll get messy, but it's pointing in, pointing in, pointing in, pointing in. And since it's messy, I'm going to pull out the arrows and then draw my imaginary ball. So here's my imaginary ball. I have an arrow pointing here, 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 and here. So in this tug of war, in this case, they're all pulling. Is that ball going to move? It stays the same. So that means they're all pushing on it equally. Since they're all pushing on it equally, they're all sharing their electrons equally, so then overall the molecule is nonpolar. So if they share it evenly, it's not going to move, so it's nonpolar. So now let's look at sulfur dioxide, SO2, so it's sulfur, 6, 12, 18, they all want 8, 24, 6, 3 bonds. Thanks, Michael. But yes, to Dylan. If the ball moves, it's polar. Thanks, Stuart. Plus 17. So this is AB2E1. What shape is this? Bent. Which means it's what? Polar. Nice. So it's polar. It's going to be bent either way. Do you guys want to see why it's always going to be polar, or are you guys fine with knowing that it's just polar? So between oxygen and sulfur, which one is more electronegative? Oxygen. Oxygen is the second most electronegative element, typically. So oxygen is slightly negative, slightly negative, slightly positive. So my arrows are going to point towards sulfur or towards oxygen. Towards oxygen. This way, and then this way. So if I draw my ball, here's my ball, and I draw my arrows, is that ball going to move now? Yeah, it makes an overall arrow. In this case, it's an overall arrow down. The ball would move down that way. So there's an overall dipole. If there's an overall dipole, then they're not sharing their electrons evenly, then it's polar. So polar. So then the next one, CH3F, Lewis dot structure, should be very easy anytime you have hydrogens or halogens. This is also AB4. Hey, look, tetrahedral. Can I assume it's nonpolar because the last tetrahedral one was nonpolar? Correct answer is no. Good. So we have to do the arrows. Between hydrogen and carbon, which one is more electronegative? Carbon. So carbon's going to be slightly more negative compared to the hydrogens. But if we compare fluorine and carbon, which one is more electronegative? Fluorine. So fluorine is more negative when we compare it to carbon. So then if I draw my arrows, between the hydrogen and the carbons, the arrow is going to be pointing towards carbon. But between fluorine and carbon, which way is it going to point towards? Fluorine. So now if I pull out the arrows and draw it on my ball right here, I have an arrow pointing down, in, and down. Is that ball going to be moving? Yeah, so polar or nonpolar? Polar. How many of you are on your phones? Just Michael? How many of you guys are on like a computer or laptop or something? Nice. No, you cannot just assume that it's polar because there's fluorine, because something like this, is this going to be polar or nonpolar? Even if it has 4 fluorines, nonpolar. So just because there is fluorines doesn't mean it's always polar. So then last one, COCl2, looks like this, COCl. What shape is this one? This is AB3, so this one is. You guys are spending too long typing. Learn how to type faster, not with your thumbs, but with the actual trigonoplanar. Then if we check the arrows, between carbon and oxygen, oxygen is more electronegative. So this arrow would point towards oxygen. And then between chlorine and carbon, Funkelbrich. Negative, negative. Right? Funkelbrich. Ooh, technically, I guess for you guys. Which one would be, is this going to be polar or non-polar? Yeah, so this one would be non-polar for us. Because all the arrows are pointing out, so they're all pulling on that ball, so it's not going to change. If the, yeah. So that's how you really do polarity problems. Questions? Some of you typed a bunch, so I don't know if you actually asked questions. How many of these are on the test? 82. So we talked about polarity and AB. That only took 21 minutes. Correct. Never trust your teacher. I don't get the E part of the ABE notation. Polarity. So the ABE notation is, so A is the central atom. B are the bonded atoms to the central atom. And E are the lone pair electrons on central atom. Right. So when you figure out the arrows, it's not saying one arrow is polar, one arrow is non-polar. You have to look at the overall arrow. So like for this one, all the arrows would point out because fluorine is more negative. So then you have to look at all the arrows together. So we have an arrow pointing up, we have an arrow pointing down, arrow pointing this way, and arrow pointing this way. So all together, they cancel out. So for this one, we have A, which is our central atom. B, we have 1, 2, 3, 4. 4 bonded atoms. And then we have nothing else on there. Why does the arrow look like a plus sign? I do a plus sign to show you that the arrow starts on the plus side of the molecule and points towards the negative side. Anytime there's two things, what are the only two ways that you could bond two things? No matter the orientation. What shape will this always make? Linear. Yeah. So that's why for anything that's two things, we just say it's A, B, and we just don't say anything else. It's just A, B. Because no matter how we rotate it, even if they have lone pairs, it's not going to really affect it because those lone pairs, there's nothing for them to get rid of, really. It's just two things. So it's just AB. So for the person who asked, like, NH. Let's go with NH. Let's see. The AB notation here would be, we have A, which is my central atom right here. Then I'm checking to see what's attached to my central atom. I have 1, 2, 3 things attached. So it's AB3, not AB2. And then we have our lone pair electrons up here. So that would be my E1. A's, if you want to put a 1 there, there's always going to be a 1. I always put 1 for the E's because some students think like, oh, each electron is 1. So that's why I always put E1 or E2, just so that students know that, hey, this is just one pair. Yeah, so this one would be polar because this one is trigonal pyramidal. All right, that one took up to 32 minutes. So next, hybridization. Someone asked for hybridization. What does S dot mean? I don't know what S slash means. All right, hybridization. Who could succinctly tell me why carbon and silicon? So carbon looks like this. This is 2s, 2p. How many valence electrons does carbon have? 4. So then it's 1, 2, 3, 4. Silicon also has 4, but it's just in the 3s, 3p. So 1, 2, 3, 4. So they have 4 valence electrons each. But yeah, it takes less energy to hybridize. So to keep these 2 electrons in the S, it takes more energy to do that than to basically kick one out and put it in the P. So in order to do that, they kind of shove all their orbitals together, they hybridize it. So now carbon actually looks like 1, 2, 3, 4. They have an sp3 orbital. And then now they make this new orbital, and they still have 4 electrons. And can I pair up electrons like this? No, you can't. So same rules apply. You have to go 1, up, up, up. So this 3 is just saying how many orbitals came from the p block. When we mash them all together, how many orbitals came from the p? 3, hence sp3. How many came from the s? 1. So technically, what number is above the s? 1. But how often do we write the number 1 in these cases? We don't, right? So technically, you could say there is a 1 up there, but we just call it sp3. So then this specifically will be 2 sp3, and then silicon will look like the same thing. Anna, but what are you confused about? Do another example of what? You always type your full name, but you go by Izzy. I always find that interesting. So only silicon and carbon can hybridize? For this class, yes. sp3 stuff. Just want to confirm it. Yeah. So like on the problem, I might ask you to show me the bonding between, like, show me this bonding, CH4. If you do just carbon's normal orbital diagram, you won't be able to do it because you have 4 hydrogens. So 1, 2, 3, 4. Each hydrogen has 1 electron. So then you'd be able to box these, but then these 2 hydrogens wouldn't be able to do anything because these electrons are already paired up. So you can't do it like this way. So what you have to do, you have to hybridize your carbon. So the carbon has to hybridize, and you make a sp3 orbital, which one electron in each. And then our hydrogens, I'm just going to do 1s, 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 1s. But hopefully you know that these are just 4 individual hydrogens. I'll just write H, 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 H. And then box, 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 box. So that's how you can make the bonding. So that's really only a question I could give you, and explaining why carbon does this or why silicon does this. See you, Stuart. What are you confused about, Alec? Diatomics. Someone tell Clara what that diatomics are. Hey, Lauren. Never have fear of ice clear beverages. What? Not polar. What? Why can't you just put the other 2 electrons in the last orbital? Because they're covalent. They're not giving up their electrons, right? They're sharing their electrons. So they can't share with an empty orbital. Yeah. Is the boxes versus errors on this test? Yeah. Remember everything we learned in previous units could be on the test. Boxes because we're sharing electrons. All right, that's hybridization. That took 6 minutes, 38 minutes. I could put converting mole stuff if I wanted to. Metallic or covalent? It depends, really. All right. What's next? All right. Intermolecular forces. Oh, here's crazy. It's on this side. Intermolecular forces. These are forces between molecules. Ionic arrow stuff. Come on. Do we really have to go over that? There you go, Michael. That's the better word for it. 10 points for you. So intermolecular forces. There are 3 of them. There's London dispersion forces. So London dispersion forces. These occur in all molecules because these are what we call momentary induced dipole. Meaning they're there for a split second. So these are also your weakest ones. So you could have something like helium is the easiest one. Helium, helium. For a split second, the 2 electrons on helium could be on this side, meaning slightly negative side, slightly positive side. Same thing here, same thing. Yeah, so electrons are always moving. So this is based on the movement. So due to movements of electrons. So as electrons are spinning around, spinning around, spinning around, Kaylee says hi. Tell her to stop licking windows. Or tell her to tutor you. She should be good at this stuff. Maybe. We'll see. So electrons are spinning, spinning, spinning. So for a split second, if these two heliums happen to just be right next to each other, and both electrons happen to be on this side, tell Aaron to help save Timmy. Preston says to study more, or I say to study more AP Bio. Do your active reading questions. So in this case, the left side of helium is going to be slightly more positive. So for this split second, the positive side of helium is going to be attracting the negative side of this helium. So then there's this small little force keeping these helium atoms together. But how long will this last? Momentarily. Because what do electrons do? They move. So as soon as they start attracting each other, the electrons move, and now they're not attracting anymore. So that's why it's constantly changing. So that's why it's really weak. So for London dispersion forces, though, bigger the molecule, the stronger the London dispersion force. Because what could happen is, let's say you have this huge molecule, like this. Somewhere, so let's say there's like a million molecules. Somewhere along the line, no, helium does not come in group of two. There's a bunch of heliums all over the place, but we just happen to take a picture of two heliums. And so London dispersion forces are happening everywhere, like this. But it's easiest if I just show you two heliums interacting. But there's heliums all over the place. So these guys could be interacting, these guys could be interacting, these guys could be repelling, these could be right here, right here, right here. So there's all over the place. So if you have this huge molecule, every once in a while, somewhere in that molecule, there's going to be some London dispersion forces, like this. But then in the next split second, what could happen to these 6 London dispersion forces right here? It could split. So then they could disappear, but at the same time, what could happen? Yeah, other ones could form somewhere on that huge molecule. It's like that. So then these ones could disappear, then these could appear, then these could disappear, then these appear. So that's why bigger the molecule, stronger the London dispersion force is. Because if we said, oh, only 2 of the molecules, they didn't have London dispersion force. Let's say these 2 pairs didn't form London dispersion forces, but all 998,909 or 9,999, 998 other pairs, they made London dispersion forces. But then if I have a group of 2 things, let's say it's just a smaller molecule of it, and I also said the same thing, 2 pairs of molecules, they did not go through London dispersion forces. What's going to happen to these 2 things? They're going to split. So that's why bigger the molecule, stronger the London dispersion force, because somewhere along here, something is going to be bonded. Because if you think about it, how strong is Scotch tape? If you wanted to tape your dog to the floor with Scotch tape, so here's your dog. You use Scotch tape to put him down. So that Scotch tape is going to be very, very, very weak, especially if you only have one. Dog will just look at you and then walk off with it. But now imagine you have the same dog. And now you put a bunch of pieces of Scotch tape on him. what's going to happen to that dog? It's not going to move. It's going to stay put. It's going to be a good boy. So even though Scotch tape is really weak, the bigger the molecule, there's more opportunities for that Scotch tape, for that London dispersion force to be part of it. So that's why bigger the molecule, stronger the London dispersion forces. So if you had questions like H2I2 Br2, these all only have London dispersion forces. That's it. They have nothing else. So then if you look at it, you would say, okay, bromine would have the strongest London dispersion force. Nope, iodine. Because iodine is the biggest, heaviest. So that could be a question you could get. So iodine would have the highest boiling point out of these three. Then bromine, and then hydrogen would be last. Yeah, the periodic table that's not behind you in the corner of the room on that blue piece of paper. So that's London dispersion forces. I guess I'll do a little bookmark for the London dispersion forces. 7 minutes. Yeah. Atomic number. Or atomic mass. Well, as the atomic number increases, atomic mass also increases. But go with atomic mass. All right, so next one. After LDF, we have dipole-dipole. Dipole-dipole means you have one molecule with two sides of a molecule, and we have another molecule with two sides of the molecule. So this is always going to occur between polar molecules. So you have to be good at figuring out if a molecule is polar or not. What happens here in a polar molecule, it's the same thing actually as London dispersion forces. It's just that this chlorine, they will always be the negative side because chlorine is more electronegative than hydrogen. Whereas if you looked at our hydrogen example, if you could still read this, why was this side of the helium negative at this moment? Why was this side negative just at this very moment? Nope, not because of the LDF. Alexander, remember, process things a little bit first and then answer stuff. Yeah, the electrons are constantly moving. So the electrons, as they move, they just happen to be on this negative side. Meaning, is this left side of the helium always going to be the negative side? No. It could be on the right side, it could be neutral, there could be, so electrons are moving all over the place. So that's why this is a momentary dipole. So this is actually still dipole-dipole because the positive side is interacting with the negative side, but it's momentary. It's there, then it's gone. It's there, then it's gone. Yeah. So for polar molecule, it's basically like London dispersion forces that are permanent. We could say like, hey, Bose relationship, right? Who else? Who else was? Oh, and Eliano's. So, because I always talked about London dispersion being forces being like high school relationship, very fleeting. With David, though, of course. So that means the negative side of this molecule is interacting with this positive side of the molecule. So they're attracting. So this right here is the interaction that's going on. So this is a dipole-dipole interaction right here, where the negative and the positive are interacting. So that's dipole-dipole. So it always will occur with polar molecules. And this is a little bit stronger than London dispersion forces because remember, London dispersion forces are basically dipole-dipole that don't last. Unlike some high school relationships. So the next one is hydrogen bonding. So this will be the strongest out of them all. And this will only occur when a molecule, so one molecule has a hydrogen, fluorine, oxygen, or nitrogen. Like that. And another molecule has a hydrogen. Then the interaction is actually between the lone pair and the hydrogen. Lone pair and the hydrogen. Lone pair and the hydrogen. So it has to be between these three elements and a hydrogen. So that's a pretty good indicator if there's hydrogen bonding. So in the case with water, let's do it down here. What's happening here is basically, I told a couple of my classes, that meme where that guy is walking with a girl, but then he's looking back at another girl. And then this girl's like, hey, what are you doing? He's like, oh, look. So same kind of idea. This oxygen right here already has two hydrogens. But what happens now is it looks over to another water molecule, and these lone pairs are like, ooh, look, another hydrogen. So this right here is the hydrogen bond. Scandalous, I know. So that's what's happening. So it's between the lone pair electrons on fluorine, oxygen, nitrogen. Oh, that's a weird name. Nitrogen with hydrogen on another atom. Does hydrogen bond the whole molecule to another? And it would rotate the other molecule. Yeah, I could rotate it, and there's hydrogen bonding all over the place. So then there could be like another water molecule here doing the same thing. Another one here doing the same thing. So all the water molecules are essentially doing it. It could be doing it with this one, like that. Teacher says that's why you can float. Like float in water? Oh. So if you fell into a vat of like gasoline, is it spelled gasoline? Nope. Gasoline. I don't know. And you fell in there, you would sink straight down to the bottom. You'd be down here, and then it'd basically be the same thing like you trying to fly right now. Can any of you guys fly? Some of you can. That's impressive. But most of you, when we try to go up, there's no resistance, right? We can't go like this, there's no resistance. But if you're in water, like the water polo kids who came back from a very long practice, Alexander, stop! Exclamation marks. We're talking about different things. So the reason why you could push yourself in water and swim is because as you're pushing, you're actually pushing against the water. The water is trying to stay together due to the hydrogen bonds. So that's why when you swim, there's actually some resistance as you swim or you try to run in water. That's why if you sink to the bottom, you could try to swim up because there's some resistance. So you could swim up like that. But for gasoline, there are no hydrogen bonds. And I'm pretty sure gasoline is nonpolar. So that means it only has London dispersion forces. So what's happening when someone's at the bottom of a gas barrel of gasoline and they try to swim up, there's no resistance. So then they go like this and they try to like swim up. The gasoline just kind of floats right by. The interaction, they just break. So there's nothing really for them to kind of swim against. So that's why if you sank to the bottom of a tank of gasoline, you wouldn't be able to you wouldn't be able to tread water or tread gasoline, because as you're up here trying to stay afloat, there's nothing really going against you. Uh, so in a sense, if you did a belly flop into a pool of gasoline, it would hurt less because the surface of that gasoline isn't as tightly held together. So belly flop into a vat of gasoline hurts less, but then you die. Belly flop into a pool of water hurts more, but tend to live. Kusha. Hydrogen's not trying to attract the electron. The electrons are attracting the hydrogen. So gasoline floats on water because it's less dense and it's nonpolar. Any quick test tips? Yeah, study. Memorize your polyatomic ions. 47 to 57, we talked about what? Dipole, and hydrogen bonding. Alec, I'm going to let you take Kara's question again. Let's see. How do you determine bond strength? So, do I have anything that's breakable here? I guess I could do this. So if you look at a single bond right here, how easy is it to break a single pencil? Pretty easy. You could break it, right? But then all of a sudden, if there's two and you have to break them at the same time, what happens to the strength of this bond? It gets harder, it increases. So then if I got a third one, put it here. So basically, the more bonds you have, the stronger the bond will be. But what happens to the length of the bond as it increases? Like single, double, triple, the bond actually gets shorter and shorter and shorter. Yeah. So next, so do you guys want like a boiling point problem? A bunch of you guys are asking about question 7. What is question 7 on the homework? Is it a boiling point problem? It makes no sense. Good job, Michael. 10 points. I'm gonna fail because I can't spell. What's crystal lattice structure? 7. Which type of compounds form? Type of structure? Ionic, ionic, ionic. Yeah, it's ionic. Crystal lattice structure looks like this. Basically, what crystal lattice is, it's actually in the notes, like Michael said. Crystal lattice is organized, geometric, orderly pattern of ions, essentially. So I always told the story like there's some salt crystals. If you got a cube of salt and you crushed it and you looked at the little tiny specks of salt, or NaCl, it's still going to be a cube shape. That is due to the fact that Na positive, when you have a little cube of salt, guess what the Na positive is going to be surrounded by for NaCl? Chlorine. But not chlorine, that chlorine ion. And guess what each chlorine ion is going to be surrounded by? I know we're typing stuff, but you should still do proper notation, like capital N, lowercase a. Na plus, Na plus, Na plus. Then each of the sodiums is going to be surrounded by chlorine. So that's why when salt breaks, salt will always break in some sort of cube shape because it'll break off in that kind of part. So that's what a crystal lattice is. Lattice is just like a framework of crystalline structures. It's basically just orderly geometric patterns that are organized. How about the second? What's the second? Why are ionic bonds the strongest? Because ionic bonds are essentially intramolecular versus all the other ones are intermolecular. Nice, Matt. Way to help Kara. Alright, so that's... Should we do a boiling point problem? Is that what you guys wanted? Alright. Sounds like you guys don't want a boiling point problem. Which molecule? Yes, rank molecules in order least to lowest. Into hope these problems work out. Let's do these three. What a problem about dipole-dipole. Dipole-dipole. I don't know. This one involves all of the intermolecular forces, so figure it out. Unfortunately, we already talked about Vesper, so you're going to have to rewatch this. Explain. So Michael got the order correct, but you should also be able to explain. Oof. You start by dancing. Thanks, Aiden. Because water definitely is not ionic. Alright, Let's go over this. So CO2, H2O, PCl, PCl3. So we have to basically figure out if they have what intermolecular forces that they have. So we look at them all. What do they all at least have? LDF. So on the test, you would say they have LDF because all molecules have London dispersion forces. So after you go that, the next strongest intermolecular force is dipole-dipole. To figure out dipole-dipole, what do you have to do? Which molecules will have dipole-dipole? Good, polar molecules. So then to figure out if it's polar or not, it helps if you do the Lewis dot structure. Lewis dot structure of CO2 looks like this. Water looks like this. And PCl3 looks like this. So Kara, what's the AB notation for CO2? Just AB2. So remember, the AB notation, A is the central atom, and then everything is describing A. B would be the two oxygens attached to carbon. Then you circled everything. I thought you meant Cl3. That's still wrong. All right. All right, cool. Let's go over stuff. So, is this polar or non-polar? The shape is linear. This is going to be non-polar because it points out, so the ball's not going to move. So, non-polar. Oh, Savvy's still here. So for this one, this is a AB2E2. E2 because of my two pairs of lone electrons. So this one's bent, automatically polar, meaning do we have dipole-dipole? Yes, we do have dipole-dipole. Then this last one, this is AB3E1. Carl just mistyped the 2 for a 3, right? Right. So that means this one is, should take a quick break to cry. Yeah. Trigonal, pyramidal. So polar or non-polar? Polar, which means dipole-dipole. So that means CO2 only has LDF. Water has LDF and dipole-dipole. PCl3 has LDF and dipole-dipole. So then, good. We also have to check the highest bond, which is hydrogen bonding. So that's the one where we're checking to see if it's F, O, or N with a hydrogen. Well, what do you know? We have an O and an H. So this one also has hydrogen bonding. So that's how you would explain it. And then you would say water would have the highest boiling point because it has three intermolecular forces: hydrogen bonding, dipole, dipole, LDF. But remember, if you should be explaining on the way why certain things have LDF, why certain things have dipole, dipole, and why certain things have hydrogen bonding. So water is the strongest, then PCl3, then CO2. Dang, we still have 29 people here. That's impressive. Because we're an hour and 11 minutes into this. Not really, just that we're all intellects. Debatable. Oh boy, the naming. Should I just pretend my internet cuts out and then it'll stop? Is there a certain time it ends? No. I always say it's scheduled for an hour, but it's never an hour. Scholars do their homework. I'll just do it like this. So, ionic naming. Who asked for this? We did a whole stinking tree mat today with colors. Do you guys want to go over how to name it, or do you guys just want a bunch of practice problems? Practice it is. All right. So quick thing about, and yeah, my table people are loud. Then you should be louder than them. I'll just give you a bunch. But to come up with some random ones, and hopefully they work and not just have random. Triorn? It's Triorn. I'm gonna guess autocorrect. All right, done? I don't know. Oh, we can't hear you? Perfect. I'll just see if you guys can hear me with the whisper. Ready, is done? 1, 2, 3, 4, 5, 6, 7, 8, 9. C. C, yes, I'm done. Multiple attendees are typing. Aiden, that's what we're doing. Sure, we are doing ionic. Not necessarily. I mixed in a bunch of problems. How dare you use the to form with me? I am usted to you. I am deeply offended. Alright, I'm gonna just assume that I'm gonna start going over this. Does anyone want me to not go over this yet? Can you move the test date to next year? I'm not ready. Of course. Alright. So W2, W is tungsten, so we write tungsten. Then you're gonna love these questions. Is tungsten in group 1? No, it's tungsten in group 2. No, it's tungsten aluminum. No, it's not. So what do we need? Parentheses. Then what's O? Oxide. Whoa. Then we have to figure out the charge of tungsten. If we do reverse crisscross, based on the tungsten, what would the charge of oxygen be? -2. And based on the oxygen, what would the charge of tungsten be? +4. And if you check your charges, does it make sense that tungsten or oxygen is a -2 charge? Yes. So that means tungsten is indeed 1b45. CuF2. What's Cu? Is copper in group 1? Is copper in group 2? Is copper aluminum? No. So what do we need? Parentheses. And when do we want it? Now. What's F? Hopefully not the grade you guys are going to get on your test. Spell fluoride correctly. It's UO. Fluoride. Based on the copper, what's the charge of fluorine? -1. Based on fluorine, what's the charge of copper? +2. Does that make sense? Is -2, Alec? So then copper is a +2 charge. Then I dropped in a sneaky sneak because when you start naming a bunch of compounds, you should always ask yourself what, just to make sure you don't name it incorrectly. You should always ask yourself if it's ionic or covalent. So NF5, is that an ionic or covalent compound? Yes is the wrong answer. Ionic is the wrong answer. Covalent. Aiden Pham, why do you know it's covalent? Two nonmetals. Good. So then we go about naming it like nonmetals. So then N is nitrogen. Then what's the prefix for 5? Penta. So it'll be nitrogen, pentafluoride. What's Fe? Iron. Is iron in group 1? Is iron in group 2? Is iron aluminum? No. So what do we need it? And when do we want it? Parentheses. Now. Good. What's PL4? Phosphate. Looks like Matt is the fastest typer out of all of you. So, based on iron, the charge of phosphate is 3. Based on phosphate, the charge of iron is 2. So what's the charge of iron going to be? 2. HI with the little g, what is that? Type, quick, type, 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 run, type, 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 type. Well, looks like Matt and Aiden don't know the answer. Who does? HI with a little g. Alec wins. Because as soon as you see, Alec, how did you know that it was a gas? The G thing. Yes, the G thing. So naming gases have their own special rule. First name is hydrogen. Change the second one to iodide. Gas. Good. So then to keep you on your toes, what is this one? Go! Nice try, Aiden fam and Annabelle Cat. You guys typed in the wrong answer. We have Alec is the winner. Ding, 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 ding. Kusho, what did you forget? The prefix. So phosphorus is a nonmetal, so then it would be diphosphorus heptasulfide. Good. Remember, never trust your teachers. What is this one? Quick, go, 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 go. Nope, nope. Correct, Aiden fam. It is just carbonate ion. Ding, 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 ding. That was also a trick because this is a polyatomic that you should have memorized. Simplify for ionic compounds. Yes, Emma, I think that's how it works. So listen to my GVLs when you're sleeping, and then you'll know everything. All right, someone name this one. Nice. Alec wins. This one is hydroiodic acid. Now someone answer this question. How did Alec know it was an acid? Ready, set, go. Nice. Alec still wins. AQ. AQ means it's aqueous. Aiden answered in a somewhat more complete sentence. So people who wanted naming practice, is this sufficient or do you want more? For the first one. The first one would be something like, I guess I could give you the name ones. All right, more practice problems coming up. Ready, set, go! I'm going to give you 1 minute to try these all out. Then I'll pick random ones at random. And then you guys will have to answer it. If you answer too early, I take off points. Aiden fam, you lose 10 points. Matt Nguyen, you lose 10 points. Michael, you lose 10 points. All right, 30 seconds left to try to get everything. Alexander Brown, you lose 100 points. All right, you guys ready? Which one is... No? No? All right. No, I can't see anything. Oh no, Christopher Kitzer. No. Can you teach geometry logic? Of course. You can only hear right now. All right, I'm going to randomly choose. Which one is... Go! Wrong. Minus 1,000 points. Wrong. Minus 100 points. I think she just came home right now. I hear her walking around downstairs. Wrong. Wrong. Super wrong because you capitalized the L of the chlorine. Wait, what does it look like I circled? I definitely circled the hydrogen sulfide gas. You did it, but not correctly. Same with you, Aiden fam. Minus 100 points. Alec with the correct answer again. So, hydrogen sulfide gas. So I know I'm going to need hydrogen. What charge is hydrogen? Positive 1. Sulfur from sulfide is what charge? Negative 2. How many hydrogens will I need to cancel out my sulfur? 2. So that means hydrogen sulfide gas would be H2S with a little g. So currently Alec is in the lead with 3 stars. Bunch of you have a negative 1,000 points. All right. Next one, do this one. Nickel 3 chloride. Go, 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 go. The winner is Alec. But yeah, you guys all got this one. So nickel has a +3 charge. How do we know nickel has a +3 charge? The parentheses. Good. Michael, 1,000,000 points for you. Chlorine has what charge? 1. Alec, +1 point. Actually, you didn't tell me it's negative, so minus 1,000 points for you. But then you were still the first one to get it correct, so net 0. Chlorine is a -1 charge. So then we crisscross. I'll need 1 chlorine to cancel out the 3, or 3 chlorines for every 1 nickel, like that. So good. Next on our list will be This one, dihydrogen monoxide. Go, 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 go. Ooh, Matt wins. H9. I hope that was a typo. Yeah, so dihydrogen is H2 and monoxide is O, one oxygen. So as soon as you see a prefix, what do you know? Well, what type of molecule is this? Go, 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 go. Matt wins. Covalence. Do. What? All right. Now do this one. Go, 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 go. Non-sulfur mononitride. Oh, Emma wins. Did you just guess correctly or did you know? S9 and good. Ooh, now it's a 50-50 shot. Unless I change the answer. Do this one that I just changed. Go, 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 go! It's tungsten 5 oxide now. Oh, now you guys all gotta think. No, no one has gotten it right yet. Nope, nope. Ooh, Annabelle with the win. And since I changed this one's worth 2 billion points. Annabelle gets 2 billion points. So, tungsten 5 oxide, because tungsten, how do we, yeah, 3 stars are still worth more than 20 billion points. So, you're still in the lead. So, my scoring system is really weird. So, there's stars, there's points, there's negative points. So, tungsten has what charge in this case? Minus a million points for Alexander Brown. Can I get a star? Nope. Minus 10 points for not answering the question. Dean Sachs gets 82 bananas. It's a plus 5 charge. How do we know it's a plus 5 charge, Dean? Minus 10 bananas because you didn't answer my question. Kyle gets half of your points, Dean, because they're parentheses, not brackets. And oxygen is what charge? Ready, set, go! Oh, Holly with the win. You get 3 stars. So then, if we crisscross, we need 5 oxygens and 2 tungsten. So it's W2O5. Nice. So last one, go! Emma with the win. Hydrochloric acid. If you didn't pre-type it, that means you're not trying hard enough. All right, what did we do? We did naming practice. Can we do more of these? Don't worry, our class will do some stuff tomorrow. Are we going to go for 2 hours? No, I'm going to stop us soon. All right, what do you guys want to talk about? Anything else? What are we doing on Halloween? A lab. So you guys are going to be doing a lab in your costumes. Oh shoot, the kids are coming to visit. Hmm. Do not think this through. How dangerous is this lab? Fire? I think we could still do it. Orbital diagrams. Why do you not give us fist bumps? You'll never know. All right, so orbital diagrams, like for nitrogen, you only care about the outer. Nitrogen is 2s, 2p, has 5 valence electrons. 1, 2, 3, 4, 5. So that to do NH3, NH3, since this is a covalent compound. Emma got you today, though. Nope, I don't remember it. No, be nice, nice. So then hydrogen is a 1s. We have another hydrogen. And we have another hydrogen. So since NH3 is a covalent compound, we're going to use boxes. I never lose. Especially in relays. That fifth period didn't want to do relays with. So you do that. Whereas if it was an ionic compound, like let's say lithium chloride, lithium is 2s, and chlorine is 3s, 3p. You would show that ionic compounds, they transfer their electron like that. So that's really just the orbital diagram for the notation to show the transfer of electrons or the bonding of electrons. We use boxes and then we use arrows. Never trust your teachers. 134 minutes to 137 minutes. Orbital diagrams. I do have a 6th period. Octet rule. Check your notes for that one. All right. Octet rule. All electrons just want a full outer shell. Not necessarily 8 electrons, because hydrogen and helium are okay with 2. All right, last question. I'm going to give you guys 1 minute to talk with each other to figure out what you guys want to talk about, and then we'll talk about stuff. Time starts now. You guys only get to ask 1 question. Sophia. All right, what's your question that you're going to ask? Depending on the question, I will end this GVL. All right, looks like we're ending this GVL. Shapes, we already talked about shapes. All right, I'm going to end the recording version of this. All right, thanks for coming. Adios.